to conclude talking about the algorithm and computational complexity, we're going to talk in this video number 13 in the foundations of computational economics about two very important algorithms for equation solving, which will come up in the course many times later. So what are these algorithms? Well, they are bisection methods and Newton-Raphson method for equation solving. Both methods address the equations of the form f of x equals 0, and we need to find the root of these equations. We'll focus on the scalar case today, although later we'll look at higher dimensional cases as well. So what is a bisection method and how does it work? It solves an equation on a given interval, a and b, under the condition that the function takes different signs on the ends of this equation. We also assume that the function is continuous, and it would be beneficial if it only has one root. Although with multiple roots, the equation, the solver will still return one of the solutions. So you can think of this algorithm, the bisection method, as binary search in continuous space. It applies pretty much the same principles of dividing the space of all possible solutions into preferably large subsections, and then focusing only the one on the one that has the solution. This is a practical video, so let's code this solver here. You can see that the input should be the function itself, the function that defines the equation, the limits, which are by default 0 and 1. Now, these next two arguments are very common for the solvers. That's the tolerance level to find the solution and the maximum number of iterations, just to prevent the possibility that the solver runs forever. And finally, there is something called a callback, and let me talk about that later. So what's the first thing to do? The first thing is to check whether the conditions for the solver are satisfied. So what do we need to check? We need to check that f of a and f of b have different signs. So let's just do this with a check like so. So if f of a and f of b have the same sign, then we have to erase the error. Which error would that be? Value error. And we should say the function has to have opposite signs at the boundaries. Okay, now that we know that the signs are different, we can proceed to our binary search in the continuous time. We will loop until a stopping criterion is satisfied. But see, because we have the maximum iteration count, let's actually organize a for loop with max iter here. And this is going to be the body of the loop. And remember, there is an else statement for the for loops in Python, which is executed if the loop goes all the way to the maximum boundary here. So somewhere inside of the loop, we will see if the error level is below the tolerance, then we say break. But if break never occurs, then we can raise runtime error to report that convergence failed to converge in so many iterations. And we can say how many iterations did we try. We tried max iter. Okay, so what should the main body of the loop do? Well, first of all, let's check if the boundaries are too far apart. How do we do that? Well, the error current error level is given by the absolute difference between A and B. And if it is satisfied, then we just break out the loop, we're done. So when we are done, we have to return the current point, which is not yet defined here, right? So let's define it as the midpoint, as in the binary search. Except now, since we're in continuous space, we don't need to do integer division. We can just take the exact midpoint. And we return the midpoint if the tolerance level is satisfied. Now, what happens if it's not satisfied? Well, then we have to check with the sign of the function again. And do it in the following way. Imagine for a moment that the function looks like this. Let me do it in new. The function looks like this between A and B. So it's positive at A and negative at B. And now we will look at the midpoint here. So if the function value, if the function has the same sign than the beginning of the interval at that midpoint, that means that we have to move this end of the interval to the midpoint itself, and the vice versa for the other point. If the function would, if the function had the negative sign here, we would move the b to the current value of x. So in any case, it is that point which has the same sign as the function value at the midpoint that we need to move. Okay, let's do exactly that. If f of a times f of x have the same sign, then a should be given a value of x, else b should be given the value of x. And I believe that's all we need to do. Let's, because, so now the tolerance is checked, the maximum iteration count is checked. Let's try to run this code. Here's an example. The function is given as a lambda function, and it says minus 4x to the cube plus 5x plus 1. The limits are minus 3 and minus 5, and we can just call the bisection method and see how it goes. Wonderful. Now, if I wanted to see what's going on inside of my solver, let's go back to this code. I would like the solver to produce some output, some intermediate output. And a very convenient way of doing this is to pass, potentially, when needed, to pass a special callback function. The callback function should be invoked by the solver at each iteration. Of the algorithm. So let's think if putting this here would be right. The question is where the callback should be initialized, should be invoked, and what do we want to what do we want to call? I'm sorry, to give to the callback function as the arguments. Well, what can a callback function be? Let's try to code it here very quickly. Callback. It will take some arguments. I don't know which yet. Let's see. Maybe x, right? And it could just print x. On each iteration, the callback function would just print x, and this is how I'm envisioning this. Nothing happens right now. That's because even though there is callback, nothing happens with the function here. We didn't run it yet. So okay, if there is callback, if callback is not none, by default it is none, then let's call this as a function and give it some arguments. Now it is possible to just do x and so forth, sort of the usual way, positional arguments. But just to make sure that the right things are getting in the right sort of places, let's make them all named arguments. Python allows that. So I would say iter equals I, x equals x. So we are giving back the information that we can. B equals b. What else? Error maybe. All the information from the inside that might be interesting to be printed. So let's let me run this, and let's run this again. Now callback got an unexpected keyword argument iter. And the fact that they are keyboard arguments is pretty good, actually, because think of this, if they were positional arguments, so they would be decided by position. So, you know, and I would say here callback of x and r, but the method gave it, you know, x, and then the second one is iter. Then you know, there could be mistakes because the arguments wouldn't match up. But this way, I know exactly that x will be a keyword argument, so x will be given the value of x exactly as the solver prescribes here, and therefore we have to do all this a equals a. But see, we're getting the mistake that the callback function, you know, we could call this function print iter, and say just to have a different name, not to get confused. This is some printing during the iteration. Now I know that all of my arguments are keyword arguments, and in Python there is a way to collect all keyword args in sort of one variable. Now this variable is going to be a dictionary, as we will see later. But nevertheless, you know, it collects all of the arguments which are not named over here, and allows us to avoid this error. And so here's the output. As you can see, on different iterations, x was moving in the following way, and the solution is x equals to -1. With f of x, remember it needs to be 0 to solve the equation. Is 0 to a certain precision. This precision, by the way, can also be changed, right? So we can say tolerance, and I'm using scientific notation here, 10 to the -10, 10 to the -10, right? And now the precision is much greater, although it took some longer time. We could say here, by the way, we could print the iteration count, and then x equals some and x, yeah, that'll do. I'm using yet another, you know, the first way to format strings here. So what is the problem? I is not defined. Well, of course, because it's not in the arguments, and I remember it's supposed to be iter, the iteration count. So here we are, iteration 0 all the way up to 35. Well, this is not really printed so well. Let's just put a lot more digits behind it, and you can see that, you know, we are converging to the tolerance of 10 to the minus 10, and that's approximately where we are here, right? 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this is our bisection algorithm, and here's an example of another use of the callback functions, where we're going to be plotting the solution. Now, it's still not yet in the course that we've talked about visualizations, but what's happening here is that, you know, we're creating a figure and we're creating a grid, and then we're plotting different things with this called PLT plot. Let me not go into details. We'll see very well what's going on. Now, see, on the plot step is going to be the callback function to the bisection algorithm here. And what this function will do, it will essentially put a line on the current x in gray color. And then by the end of it, it converges. It reports in how many steps it converges. Yes, here's an important point. So remember that everything in Python is an object, and so this function is an object too. And we just said that, you know, let's create an additional public attribute to this object, to this function, and call it a counter. And so this will be incremented at every call of the function. And it will essentially just hold the number of functional calls, or the number of iterations rather, the number of times this function was called. Okay, let me run this, and what do we see? Let me go to the other view, the normal Jupyter Notebook view. Here's the graph of the bisection method. What happens here? Well, in red we have the function. Here's the solution, the zero of the function, the crossing with the black line that we've also plotted. We've plotted the zero line. If you remember, the initial boundaries are -3 and -0.5. So this is where the graph is shown. Now the algorithm proceeds in this way. The first midpoint is -1.75, which is here. And because this point of the function is of the same sign as the left side, then the next interval to be considered is this interval. The midpoint there is somewhere here, and the next interval is this. The midpoint is here, the next interval is this. And you can see how the interval shrinks in each step of the algorithm until we converge to the solution by checking that the difference between the sides of the interval is not larger than the tolerance. And this is the convergence criterion. Okay, now let's look at the Newton-Raphson method. Let me go back to the slides. It solves the same type of an equation, f of x equals 0, but using a quite different approach. It's worth mentioning that you can use Newton method to also solve the maximization and minimization problems by solving the first order condition. So the idea here is that the method has to start at some initial point, x0, and then it takes the steps, which is known, a series of steps according to this formula, and this is known as a Newton step. The iteration continues until convergence. So what is this Newton step, and where does it come from? Well, if we write a Taylor series expansion around the solution, f of x, let's think of f of x as being a solution, the root, so that's 0. And then imagine that we are looking at two consecutive approximations of this solution, xi and xi plus 1. And we just plug it in, use the first two elements of the series, and we have this formula from which we can express xi plus 1, the next point in the sequence of approximations and get exactly the Newton formula. Let's code it up and see how it performs. So let's look at the start here. Because of the derivative that is included in the Newton step, we have to pass to the function both the function and its gradient, so the derivative of its function, the initial value, and then as before tolerance and max iter, and as before we'll have a callback. All right. So let's start with the main loop. So for e in range of max iter, there will be something happening here, and then if the loop, if this for loop goes all the way to the maximum iteration, then we erase a runtime error failed to converge in so many iterations. And how many? That's max iter. Okay, what do we have to do in the loop? Let's calculate x1 as the Newton step. X0 minus f, it's called fun of x0 divided by the grad of x0, and I'm assuming here that both fun and the grad are functions. And now we can calculate the error, the current error of this convergence as the absolute difference between the x1 and x0. Okay, if error is less than tolerance, then we can break out of the loop. And what does the method return? It returns the current value. Well, let's return the x1, the next value. But if it doesn't break, what happens then? Then x0 should be updated with x1 so that the loop is ready for the next one. And here I left some space for the callback. So if callback is not none, then call this variable as a function, and here we have to think what to give it to the callback. Well, x0 probably, x1, error, iteration, what else? That's all probably. Okay, let's try to run this. Here's an example. So f is the same function, minus 4x to the cube plus 5x plus 1. Its derivative is given by minus 12x to the square plus 5. And now we can run a Newton method. Well, let's see. Let's give it all the default number of iterations, which is what? 100. And default tolerance. We're starting from negative 2.5 and just print the solution in the end. Well, the solution is x equals minus 1, and the function at that x is exactly 0 or 0 to a certain precision here. And remember, we were solving the equation, so this is what we expect. This is good. Now, let's do a similar thing to what we did before, and with bisections. And define some sort of the print iter function here. There's a bit of a problem that there is no x. Instead, there's x0 and x1. And let's print them both. So this is where we're going from. We're making the Newton step from. And here where we land. Let's see. Oh, of course, nothing happens here. Why? Because we need to call Newton method and pass this function as the callback. And here we are. So you can see that we start with minus 2.5 and jump to minus 1.77. Then from 1.77 we jump to minus 1.33, 33 to minus 10, and you can see that it comes to this one with many zeros in just 6 iterations or 7 iterations. That's actually much faster than the bisection method, but maybe it's just because I didn't give it the tolerance. So let's give it the same tolerance here. Same tolerance. So that should be given as an argument when we call the Newton solver. Well, no. It also... well, no. Look, it takes one more iteration. One more iteration to go to 10 minus 10. 7 iterations to 10 to the minus 6. 10 iterations to 10 to the minus 10. Okay, that's interesting. How about graphing? Here's a prepared piece of code which creates a series of graphs, and let me just run it. Here you can see that the callback that plots the step is actually quite involved. It only works for the first 10 steps just to avoid having many graphs, but as we saw in 10 steps, Newton actually converges in this example. And we'll be plotting different things. Function, the 0 line, the x naught, that's where we're taking the Newton step. And this is a vertical line, by the way. And then we plot the function which is a tangent to the f at the point x naught. This is actually how Newton is defined. So let's run this, and let me go to the normal notebook view. You can see here that we're starting with minus 2.5, and the step that Newton is taking, here's the next step, is actually defined by the crossing of the tangent line at x naught with 0. So you can think of Newton as being a series of linear approximations to the function. If the function was linear, then we would, at this point, we would arrive at the solution immediately. But because it's not, then we have to take another point. And again, we're doing a linear approximation and jump to this point here. And from this point, we jump to this point and so forth. And after about, what, 4th iteration or 5th iteration, it's hard to see any changes in the picture because it's now, well, becoming out of scale. Okay, here's my... implementation that I wrote when I was preparing for this. All right, so these are 2 methods, and we will come back to them many times during the course. Let's let's explore in more details the rate of convergence of both of this. We've already noticed that Newton seems to be working faster. Well, how fast solution converges, the approximation converges to the true solution is the rate of convergence, and it can actually be approximated by looking at the rate of decrease of the error in the stopping criterion. The important fact to remember is that bisections have linear convergence, and Newton method has quadratic convergence. It's much faster. This is related to the computational complexity, but let's first check this convergence rates. So look here, I'm going to be using this function as a callback function. It's called print error, and the idea is that we are printing the number of iteration, the current x, and the error that is corresponding to that x. Now, a little bit of additional work that we need to do is to figure out whether we have x or x naught in the arguments that are passed to this callback function. And of course, different bisections only passes x, and Newton method passes both x naught and x1. Well, we're going to treat this double star KW args, and this is the standard syntax in Python in passing a whole dictionary of arguments. And we will check whether x is in the keys of this dictionary. If it is, then we will use x to initialize this variable. Otherwise, we're using x naught. Okay. And then we can just run Newton and bisection to the same tolerance level, 10 to the minus 10. This is the same problem and same initial conditions. And you can see that Newton converges as before in 8 iterations to the tolerance level of 3 times 10 to the minus 14, whereas bisection method, it takes, 35 iterations to reach the required tolerance level of less than 10 to the minus 10. Well, the important thing to notice here is that if you look at this error and the rate at which it decreases, I've purposely had written this in the scientific notation, which is, by the way, given by this expression here, 8.6 e. That means take 8 spaces to represent a number in scientific notation e with 6 decimal places. So that's what we should have here. Well, if 8 is not enough, then it takes more space, but it's not that important here. 17.14f, that means, standard floating point representation, the decimal dot, with 17 places and 14 digits after the decimal point. Okay, look at the speed of convergence. At the rate of decrease of this discrepancy, the error. With bisections, you can see that it's sort of slowly decreasing, and it loses the magnitude of at steady pace, I would say, right? So it goes from 0, then to 1, several ones, -2, -3. This is 10 to the minus 3, 10 to the minus 4, 10 to the minus 5, and so forth. The goal is 10 to the minus 10, of course, and here we've reached the goal, and that's where we've converged. Now look at Newton. Newton first is kind of slow. 7 to the minus 1, 4 times 10 to the minus 1, 2, slowly decreasing here. But then, at some point, it just starts doubling this precision from 2 to 4, from 4 to almost to 7, right, and from 7 to 14. And this is what's referred to as quadratic convergence of the Newton method. Once the current approximation, current x naught, is in what's called the region of attraction, the domain of attraction of this problem, then Newton method converges extremely fast to the very precise solution. Now, thinking about the complexity of these solvers, we have to think what's the size of the input, what's the size of the problem. And the right way to think about it is that the size of the problem is the desired precision of the solution. That's essentially given by the tolerance level that we want to achieve. And therefore, the attention to the errors in the solution is for this algorithms is so important. Now, it is true that the rate of convergence is part of the computational complexity, but it turns out that if we think of the computational complexity, say, of Newton method, then it turns out to be related to the log n, but it also has to be multiplied with this additional factor, which takes into account the cost, the computational cost of computing the entity needed for the Newton method, namely the ratio of the function evaluated at a particular point to its gradient. And this actually is not, and it needs to be done with the certain precision as well. So this is actually not a trivial component, especially for the multidimensional problems, which we will look into later in the course. But in general, you can see that quadratic convergence rate of the Newton method somewhat relates to the log n computational complexity of this solver. Here are some further learning resources where you can sort of dive deeper into the computational complexity of Newton's solver. The bottom line for us is that Newton Newton solver is a very, very fast solver, and much faster than many other schemes, even the better ones, such as binary search or bisection method here. All right, till next time.